All right. Hello, everybody. Welcome to today's installment of the Corundum developer meeting. Let's go ahead and take a look at the agenda here. I just have announcements and then the normal status updates. All right. So announcements. The next developer meeting will be, I think, August 6th. Let me just double check on that. Yep. The next Switch meeting will be July 9th, a week from now. I don't see Carlos online at the moment, but if he's got stuff to talk about, then we'll have the Switch meeting in a week, as usual. At the next few meeting times on here, people take a look at. There should be Google Calendar linked on the wiki page. But yeah, the idea with the current developer meetings, first Wednesday of every month at 9 a.m. The Switch meetings, second and fourth Wednesday of every month at 9 a.m. PDT. Although we'll skip over the Switch meetings if Carlos doesn't have stuff to talk about for whatever reason. Anyway, moving on to status. All right, so the main new things here are the low latency mode, right? I have that working, and I also have a 32-bit Mac and PCS set up, both with the normal latency, with the asynchronous gearbox, and with the low latency synchronous gearbox. I also put together just last week a 25 gig Synchy demo with the synchronous gearbox. So I basically took the old 10 gig Synchy demo with Corundum, ripped out the 10 gig Mac or the older 25 gig Mac and replaced it with the new 25 gig Mac and rebuilt the clocking components necessary for DDM-DD to work and did some testing. It works, but it needs some tuning. So we'll see some plots on that. Talk a little bit about the next generation version of Corundum. Planning on making a couple of different versions with slightly different optimizations. And then I'm also starting work on a new FPGA-based network stack that I'm calling Zircon. Initially, it's going to support 10 gig, but eventually it's going to support at least 100 gig, but hopefully up to 400 gig as well. So more details on that in a bit. All right, so just blow through some of this stuff that that I've talked about previously, just to make sure everybody's on the same page. Basically, I'm deprecating all of the existing MIT licensed HDL code. All of this stuff is going to be basically superseded by the Taxi repository. So the great thing about that is that if you're interested in using this for commercial applications, you'll be able to get support and whatnot. If you're using it for open source research, whatever, you're welcome to keep using it under the CERN OHL license that's attached to the Taxi repository. And the hope is that the licensing fees for commercial use will go to the long-term sustainability of the overall project and support continued development and that sort of thing. So if you're interested in this for commercial applications, please reach out. Happy to discuss further. All right, so as part of this, I'm taking all of the existing HDL code and rewriting it, translating it, etc., into System Verilog. Done a bunch of stuff for AXI Stream, AXI Lite, and AXI so far. I need to probably circle back to that at some point and port a few more modules. PCIe stuff in particular is still a rather large to-do item. I've been putting together a bunch of new wrappers for 10 gig, 25 gig, basically taking a lot of the ideas from what I ended up doing for Corundum and bringing that back over into the Ethernet Max upstream. And that's looking pretty good at this point. I've also added example designs for several different boards, mainly around these new wrappers. All right, so the porting progress, I've done most of the AXI Stream stuff. Pieces of the AXI and AXI Lite code. I think I've done all of the low speed max, the 10 gig, 25 gig max, timing stuff, low speed serial, that sort of things. To do in the short term, the new IP stack that I'm working on now, a lot of AXI and AXI Lite stuff, the remainder of that, the DMA and PCIe components, and I've been putting together some new sync primitives kind of off and on. So hopefully I'll be able to get that finished up pretty soon as well. I know I've been using the sync primitives more in modules that I've been porting over as opposed to the ad hoc approach that I had before, where everything kind of had their own local synchronization stuff. Now that it's all a unified library, it's more reasonable to have shared modules for that sort of thing. All right, so I put together example designs for all the Ethernet stuff. That's basically just back-to-back Macs. But the idea is that once I have some of these, more complex subsystems, I'll add basically subsystem specific example designs that have, diagnostics and sort of a representative thing that you can, build on top of. I was originally thinking about doing kind of kitchen sink example designs that have like everything. And there is something to be said for having that because you can just build it once, load it on the board, and test all the different capabilities. But on the flip side, if you only need one or two things, it can be somewhat difficult to figure out what's relevant and what isn't. So by keeping stuff simpler, that should make things hopefully a little bit easier to use. All right, so moving on to the new MacFi and GT wrappers. The new wrapper modules that I've been putting together, they basically integrate the GT core along with the Mac and the Phi logic all in the same set of modules. And I have provisions to actually support simulating that in Verilator and whatnot, where you have to exclude the GT core instances and then feed the test data in directly to the Phi layer components. These are built with a much more modular design, so I'm using the CDC primitives. I've also put together some separate modules for, reset management and whatnot, reset sequencing, and timing of all the various components. So all that looks pretty good at this point. I've also updated, let's see, so what did I do? No, so I have multiple GT wrappers that support running the GTs in different modes. So for example, I have, originally I just had a one wrapper for the asynchronous gearbox mode at 64 bits. So I've added new ones for the 64-bit synchronous gearbox as well as 32-bit synchronous and asynchronous gearboxes. So all of those main modes are covered now. To do is like the DRP interface logic and supporting, higher and lower line rates. It'd be great to be able to dynamically switch between, 10 gig, 25 gig, and 100 gig, right, by having the CMAC core in there and wiring that up. So that's not supported yet, but that's something that I would like to do at some point, as well as auto negotiation, SGMII, US XGMII, and 1 gig support. So all that's kind of a longer term to do. All right, so let's see. I've talked quite a bit about this in terms of the 10 gig, 25 gig low latency mode, where you can run the transceivers in the synchronous gearbox mode. So this doesn't really change too much in terms of the actual logic, but what I've done is I've added a config low latency parameter to the top level MacPhi and GT wrapper. And basically, if you set that, it will switch which channel wrapper it's using between the synchronous gearbox and the asynchronous gearbox version. So in the low latency mode, it will use the synchronous gearbox, and then it will enable all of the supporting logic for the synchronous gearbox in the Mac and Phi components. And that'll result in not only somewhat lower latency in the transceiver, but also, more consistent timing performance with the through the gearbox, because we can actually track that state. So for PTP and whatnot, you'll get better performance, and this will be necessary for White Rabbit in the long run. There is a little bit of a timing and area trade-off. Since some additional signals are required for the gearbox logic, it's gonna use up a little bit of area, a little bit of additional area, and then also it runs at a slightly higher clock frequency. So that could be a problem if you're on a slower part or a very full FPGA. So I'm leaving this option around in the case where, running at this higher speed with the higher resource consumption ends up being a problem. So you can just turn it off if you don't need it. All right, so for just a little bit of overview here, what's the story with the low latency mode? What's the difference? This is mainly in terms of the gearbox. So what's the gearbox? Well, for line codes like 64, 66, the code operates on 66-bit blocks. And generally, you can't build a 66-bit wide serializer. It's going to be a power of 2 plus maybe 5. But 66 is 2 times 3 times 11. So that 3 and that 11 are kind of a pain. So you're not going to find a serializer that's 66 bits wide. but you want to be able to work 66 bits per clock in the fabric. So what you need to do is use the 64-bit SerDes and repack 64 bits into 66 bits. And the component to do that is called a gearbox. But the problem is, because you're repacking 64 into 66, you start needing install cycles, right? Because you can't transfer, if you're transferring 64 bits in and 66 bits out on every cycle, well, eventually you're going to run out of bits, right? On that first cycle, you don't have the full 66 bits to transfer out, so you have to stall for a cycle, and that complicates the logic. So synchronous gearbox, the data path has to stall. Then also the effective latency varies cycle by cycle because you have a different number of bits stored inside of that gearbox, but you can potentially track that and correct for it. With the asynchronous gearbox, they add a FIFO and use a different clock division to absorb the stalls in the FIFO. So the interesting thing actually is that the latency is effectively constant cycle by cycle with the async gearbox, but you can't really measure it, and it varies between resets and link disruptions and whatnot. So while the async gearbox is great for getting something up and running quickly, running at a slightly lower clock frequency, it does have this problem where the latency is going to be higher, and the delay through it is going to be difficult to deal with, especially if you're trying to do stuff, white rabbit level on the picosecond level. That just doesn't work. So to deal with the synchronous gearbox, I wanted to come up with a mechanism that was somewhat independent of the specific gearbox in use. Instead of like baking the sequence into the modules, it makes more sense to somehow have the transceiver indicate what the sequence needs to be. So you basically, in the receive direction, it's easy, right? You just have a valid signal, right? And you propagate that down. It's not a big deal. It's in the transmit direction that things are more complicated, because you have to generate this stall sequence on the correct cycles with the correct gaps and whatnot. So what I decided to do is basically create a loop from the GT or logic in the GT wrapper all the way up through the MAC and PHY layer logic, and then back down to the transceiver. So there's a gearbox request stall and gearbox request sync signals. So the stall request, every time this is high, the MAC and PCS logic has to stall for cycle. And then there's the sync signal that indicates the start of the sequence. And this is important just to make sure that the transceiver will be synchronized properly with the sequence. Let's see. Right, so you have the request signals going into or coming from the GT, going up to the MAC and PCS, and then you have signals coming back down. Basically, the MAC and PCS logic has to forward it with a constant latency, so everything has the correct alignment at the transceiver. And then for the Xilinx GTH and GTY transceivers, there's a TX sequence input that's basically just a counter. It increments either every cycle or every other cycle. That has to be generated in synchronization with the stall sequence. So there's a little bit of additional logic that generates a TX sequence based on the synchronization signal back at the transceiver. So when you run it on the FPGA, this is what it looks like. We have the stall request from the transceiver. That goes up to the MAC and PHY logic. Here's the stall when it comes back out, right? You can see T-valid, or not T-valid, but the TX data valid low for 2 cycles. And the data is held for an additional 2 cycles. Here's your start pulse, and then the start pulse aligns with the TX sequence starting at 0. So with all this done properly, this thing works on the FPGA, and I've tested this both at 10 gig and at 25 gig with a few different frame sizes with my network tester, and everything seems to work properly. Right. So the main data path modifications for this are complete. Longer term, I need to make some adjustments to the timestamp values. So as of right now, it does work for sending and receiving data, but if you want to do time synchronization, there's some modifications that need to be made that I have yet to figure out the proper approach for that, because you need to do the timestamping basically as close to the PCS layer as possible, because the timestamp correction needs to take into consideration the current gearbox state when that data is handed off to the transceiver. So getting that right requires logic that's going to be specific to the transceiver, and I need to figure out the best way of actually, doing that handoff, both for RX and for TX. Longer term to do, maybe it makes sense to make like an ultra low latency, setup with a fabric gearbox, because I know the Xilinx gearbox and the GTH and GTY transceivers have a cycle or two kind of extra latency that's not strictly necessary. So that could potentially be removed. You might be able to combine the gearbox logic with some of the other PHY logic. I'm not sure. That's potentially something to mull over. But I mean, from my perspective, it's the raw latency is not particularly important for anything that I do. It's more in terms of the latency variance. So somebody is interested enough in that to, fund it, potentially we can go that route. Otherwise, we'll probably roll with what I have for now. I did take a look at 7 series support, but due to some differences in how the FPGA clocking primitives work, it's unclear what the best approach is going to be on the 7 series. Because the naive approach is going to eat up all the clocking resources on the entire chip very quickly. So I need to do some more reading on the manuals and probably some synthesis tests just to see what's possible there. So we'll cross that bridge a little bit later, probably. And there's also some differences just in terms of how the transceiver wizards and stuff work that make things slightly annoying on the 7 series. Like, it seems like it's not possible to just generate the bare transceiver core and then step and repeat that in the HDL. So either you got to instantiate the primitives directly, which is doable but annoying, or you have to pull the transceiver core out, and that's also annoying. So we'll see. I got some ruminating to do on the 7 series. So if somebody's asking for it, then we can look into it. Otherwise, that's probably going to get tabled for now. All right. So 32-bit Mac and PCS. Now that the synchronous gearbox support is working, adding support for the 32-bit operation is actually not that much additional work. The idea with the 32-bit support is that it provides a smaller footprint and a lower latency, but it only supports 10G because of the higher clock frequency. So I've gone ahead and I've added 32-bit support to the PCS and to the Mac and PCS logic, supporting both the synchronous and the asynchronous gearboxes. I also added 32-bit transceiver wrappers, and I've tested this currently only on the ZC106, but it should work on other parts because the transceiver configuration is basically the same. It's like previously with the 25 gig stuff, there is a difference between the GTH and the GTY in terms of how the clocks are configured and a couple of other minor things. So it's like, say, with the synchronous gearbox, they have a different sequence between the GTH and the GTY if you're running in 64-bit mode. But in 32-bit mode, they're configured the same way. So ostensibly, there shouldn't need to be any changes necessary, but I have not yet tested it. I also have not tried to characterize the latency. I know somebody was doing some measurements on the other cores, but I don't think they've rerun the measurement on the 32-bit core yet. So it would be interesting to see what that looks like. I did notice on my network tester, it did show a somewhat lower number. I would need to run it again to see exactly how much. I think it's shaving off another 50 nanoseconds or so, which, is respectable. But I think a more careful measurement is going to be necessary. All right, so for resource consumption numbers, just for kicks, basically there's about a 50% savings in LUTs and about a 25% savings in flip-flops per core. And this is also cutting the data path width in half. So presumably, if you're going to compare the logic sitting behind that, you would see similar savings in terms of LUTs and flip-flops when you strip out all of those additional bits. But like I said, the flip side is that this is working at double the clock frequency. So that's potentially problematic depending on what you're doing. I've updated all the 10G example designs to use the 32-bit configuration. So, and by 10G example designs, I mean all of the boards that only support 10G and don't support 25G. I might do another pass and update some of the boards that you can select between 10 gig or 25 gig to use the 32-bit in 10 gig mode, but we'll see about that. That'll require a few additional modifications to make that work. I think in principle, it shouldn't be that much. I just need to pull out that. I just need to pull out a couple of parameters, I guess, and have a config.tcl file for those projects. So it shouldn't be a big deal. I'll do that at some point, probably. All right. So the next thing that I did, this was just last week, is I basically took the 10 gig Synchy demo and I swapped out the old 10 gig Mac, or I guess, well, the old 25 gig Mac with the new 25 gig Mac. Um, it's a bit of a hack job. So right now the Macs are not actually usable for data, only for timing, but that should be sufficient. And I configured it for 25G with the synchronous gearbox, just to get an idea of what the performance looks like. I also switched to using LR4 optics instead of CWDM4, and I added 3 kilometers of fiber just to see what happens. Is this thing going to be detecting the temperature of the room based on, as the fiber expands and contracts, that'll change the timing. So yeah, that worked. It now acts like a thermometer. So that's like a very expensive thermometer. But that's indication that this thing actually is doing what it's supposed to do. So that's good. The PLL loop works. I had to do some retuning to get it to close properly. But the DDM-TD output is a bit noisy. And now that I've been looking at it more recently, there's seems to be some other instability thing where things are jumping around in ways that don't make sense. So I need to take a look and figure out what's going on with that. Definitely is in need of some tuning. This is what the 10 gig Synchy demo setup looked like when I put it together initially. We got a couple of Alveo U200s. This is with the CWDM4 modules. The current setup I have now is basically the same thing, except these now have blue tabs instead of green because they're the LR4 modules. And then I added a couple of these little 1.5 kilometer fiber spools. What do they call them there? The OTDR dead zone eliminators, basically. So they've got 2 FC connectors on there. I put one on each side of the link. So otherwise the same setup. It's still got the HD4 delay line in here. So with the 10 gig demo, it looks like this. What I did is I have a little script that controls the fiber optic delay line to step it from 0, -10, 0, -9 picoseconds, so on and so forth, all the way up to 0, +9, 0, +10. So with this, you can definitely see that there's, I don't know, it's about 10 picoseconds or so worth of noise peak to peak, which is pretty respectable. You add a little bit of averaging on top of that, right? The red curve is just an average version of the white, which is the raw data. And you can very easily pick out steps of even just a couple picoseconds. Here's 10, there's no problem. 9, 8, 7, 6, 5, 4, 3, 2, 2 or 3 picoseconds seems like it's not hard to pull out of this. At 25G, it's a slightly different story. First thing is you note the slope, that's the temperature changing. So I guess I should probably redo this without that without that fiber, and just to get a cleaner picture here. The noise is also quite a bit higher, right? So instead of being like 10 picoseconds, this is what, like 30 or 40 picoseconds. So there's definitely some differences in terms of the clocking setup, feeding the DDMTD samplers. So like with the previous setup at 10 gig, I was using the asynchronous gearbox. So the internal logic ran at 156 and the reference clock is 156. So I could just use that directly and then generate the offset clock. In this case, the whole shebang is running at 400 and something, right? 403, 402.8. I can't remember what the exact number is. You get this big long decimal on all these things. I can never remember what all those digits are, but it's like 403 megahertz or something, which is very different from the external reference clock. So you have to multiply that up with an MMCM, and it's possible there's that's not configured quite right, and or it's adding jitter. So that could be affecting the noise here. I'm gonna have to mess around with that configuration a bit. It's also possible there's other stuff going on. So this is kind of the first time I've ever tried this. So we'll have to iterate from here and see if the performance can be improved. The other thing that I was thinking about as well is that as I'm looking at implementing some of this higher precision timing stuff, it's better to do everything at the same frequency if possible. So the original idea that I had was to support 3 or 4 different reference clocks depending. So for 10 gig only ports, you can do 32-bit 10 gig at 322 megahertz. For 64-bit 10 gig on a 25 gig port, you do 161. For 64-bit 25 gig, that'd be 402.8. And then for the Xilinx CMAC, they do 25 gig at 80 bits, which is 322 megahertz. So being able to support all of these and being able to do the DDMTD, phase measurements would be necessary if you wanted to do White Rabbit, with this configuration. But what I realized later on after some discussions with CERN is that, if you can get everything to run at the same internal clock frequency, even if you need some additional logic, then that is potentially going to give you improvements on the timing side. So if we put together some custom async gearboxes to get from either 32 bits or 80 bits to 66 bits, potentially in a different clock domain at like 400 megahertz or something, then you could potentially do 32-bit 10 gig at 322 and 80-bit 25 gig at 322. And this means that if you have 322 on the board, which you could potentially get in a lot of cases by reconfiguring the programmable oscillators on there, then you can get potentially quite good performance without having to do a bunch of frequency translation, or without having to support, some sort of fractional DDMTD mechanism to deal with some of these intermediate frequencies. So this is potentially quite an interesting approach. I'll probably be taking a look at this at some point to see how realistic it is to build, these fabric gearboxes. But yeah, that could be interesting. All right, so moving on here to the next generation version of Corundum. So, like I said before, I'm basically deprecating all of the original MIT licensed code and transferring everything over to System Verilog. So, what does that mean for Corundum? And what I'm thinking about doing is building basically 3 different variants with rather different optimization parameters. So the first one is Corundum Micro. This is intended for like SoCs, just as a little block you can drop down. Size optimized, supports a few ports of gigabit Ethernet. Corundum Lite is basically going to be kind of similar to the current version of Corundum. It supports a handful of ports at 10 gig, 25 gig, so maybe about 100 gigabits per second aggregate bandwidth, something like that. And then Corundum NG is going to be kind of the highest possible, no holds barred, maximum performance, 100 gig to 400 gig, or like multiple ports of 100 gig or one port of 400 gig, that kind of thing. The plan is for all of these to use the same driver and to support timestamping, checksum, and segmentation offloading. So I'll go into these in a little bit more detail. Corundum Micro, the whole point of this is to make it as small as possible. Handful of ports at 1 gigabit per second. Because at 1 gig, we have lots of cycles per packet, we can do kind of a micro-coded design, either with the softcore type thing or just with the state machines. It's intended for, like a SoC type application. I mean, not necessarily Zinc, but, maybe like a RISC-V type core or something like that. But it could potentially also support PCIe. Probably only 1 lane, you don't need that much bandwidth for this. The plan is to support basic NIC offloading like segmentation and checksum offloading, scatter gather DMA and timestamping. Although I have been scratching my head over, like, if you want to do something like checksum offloading, if you have to read the entire packet and then checksum it and then send it, then that potentially bumps up the size if you're trying to keep the the internal buffering low, right? If you don't do checksum offloading, then you don't even need to buffer the whole packet necessarily, especially if you're just talking about 1 gigabit per second per port. So I have a couple of potential ideas, like you could read the packet twice. You do the checksumming on the first round, and then on the second round, you actually send it after inserting the checksum into the header. But yeah, not sure about that. And potentially you could support a couple different modes depending on how you want to optimize it. But the idea behind this is it's not going to be like a top level design like the current version of Corundum. It'll just be a little core you can drop in. But the main thing here is I think it could be a good method for prototyping the new descriptor format and hardware interface, queue-based interface, and do the initial driver development and get a lot of the kinks worked out of the whole system, when we don't need to worry too much about the performance. And then obviously the next step is to build a design that's higher performance. And if you already have a driver that basically works and you have a lot of the internal interfaces more or less figured out, then hopefully that'll be a little bit easier. So for Corundum Lite, the idea is to support a handful of ports at 10 gig, 25 gig, maybe 1 port at 100 gig. We'll see. Aggregate bandwidth probably 50 to 100 gigs, something like that. It'll support multiple TXR queues, SRIOV, PCIe, and AXI. Potentially it'll support things like PCIe AXI dual head. So if you have like an MPSoC board that has PCIe on the edge connector, then this could be an option. I don't know if it'll support an application section. I'll think about that. And likely this will be available as a self-contained core that you can just drop down. Especially when you're using the MPSoC stuff, it makes sense to have an option for that because it'll just be one block in the big old block diagram. And there's definitely other people that like using the IPI flow, so it makes sense to try to support that. And then Corundum NG, the idea with this is it'll support up to 400 gigabits per second. My plan is to target the Intel Agilex I-Series R-Tile natively. We'll see how realistic that is because at 500 megahertz, that's pretty zippy. So I don't know if that's going to be, I don't know if that's going to be realistic, but that's kind of the aspirational goal anyway. Potentially it could support multi-headed PCIe for, dual Gen 4 or 5 by 8 mode. I know the Versal devices, CPM5 is, they support Gen 5, but only by 8. So if you get like I think the V80, you could do Gen 4 by 16 or dual bifurcated Gen 5 by 8. So being able to support that dual bifurcated mode might be useful. And I'm also thinking this will support PCIe AXI dual head. So for things like a Versal device, to bring the ARM cores online and have them interact with the design as well, that could be a pretty useful technique. And this one will also likely support, some sort of local DMA for talking to DRAM, HBM, that sort of thing. Details on that are somewhat TBD at this point. And this one will definitely support an application section if you're using it as a top level design. All right, so now the next thing, or the last thing, I guess, for today is the new network stack that I'm starting to work on called Zircon. And basically, the old UDP/IP stack that I wrote in the Verilog Ethernet repository has some significant limitations. There's a lot of things about the design that I don't really like. And I think there's probably quite a few bugs lurking around in there. And that stack also was never really fully parameterized. So it really only supports, like 8-bit 1 gig and 64-bit 10 gig / maybe 25 gig if you get it to close timing. So the idea is to build a more flexible replacement that potentially can support, higher link rates as well as filling in like 32-bit support. So the core stack is going to support IP and UDP natively, but then have some sort of a mechanism for supporting protocols like TCP and RDMA that add some additional components on top of the core stack. The plan is to have something a little bit more, socket style at the user logic level. So instead of having to, keep track of addresses and stuff, the idea is you'll have some, context information that you would pass on, TID or TUser or TDEST or whatever. And then the stack will deal with the headers and then attaching the payload and the headers together, which should make things a lot easier to deal with. And it'll also support multiple internal clients, so you don't need to deal with multiplexing yourself. The configuration will be both via commands on streaming interfaces as well as via an optional register interface. That's the long-term plan anyway. Short-term, we might not support the register interface initially. We'll see. ARP, NDP, and other supporting protocols will be handled by either some sort of a soft core or some sort of a, packet processing state machine. Instead of, unwrapping everything. So it makes no sense to build, an ARP core that's capable of, 25 gigabit per second operation when you're going to be getting like, a few ARP packets per second, We can do something that's a little bit more compact. It seems like there's a good chance that embedded RDMA is going to be on the roadmap, but we'll see about that. More details on that later, hopefully. I'm thinking if this works correctly, then this can potentially be integrated into Corundum to support things like SRIOV, RDMA, TCP offload, things of that nature. And basically by doing the packet processing side of things, and then it'll connect with the existing data path in Corundum for interfacing with the host. So just as a quick example of how I envision this working on the client side, the idea is there's going to be separate streaming interfaces for each client, so you can parameterize, how many internal clients you want. And then on each of those clients, you can potentially have multiple connections being used at the same time. And for each client, there's going to be 4 streaming interfaces. There's TX and RX data, TX and RX control. The control interfaces are used to interface with the stack. So you will send commands with a particular format that can do things like open a connection, close a connection, perform an ARP, address lookup, that sort of thing. And then also if you've opened an address for listening, then if there's an inbound connection on that port, then you'll get a notification from the stack saying, hey, there's an inbound connection. Here's the remote IP address, et cetera, et cetera. Then the data interfaces will carry the packet data. And the idea is that you can cut the headers at a configurable point. So if you want just the UDP payload data, then you can do that. If you want IP packets and you want to drop the Ethernet header, then you can do that. And that goes for both receiving and transmitting. So depending on what you're doing, what you want to follow the stack up with, the user logic, there's potentially multiple options for how to handle that. All right, so real quick example of how this works or how I envision this working for UDP. If you want to send a UDP packet, what you will do is send a request on the control streaming interface to open a connection. So you specify like the destination address and the port. The stack will then assign a source port and return context information saying, use this TID value when you want to send to this destination, basically. And then the stack will perform an ARP lookup request, if necessary, to get the destination MAC address. And then you can just issue the payload data to the TX interface. And then the stack will, if the ARP operation has completed, it will then build the headers and send the frame. If it's still waiting on that, then that client interface will be blocked, but the other ones can continue operating. So that's kind of high level how that works, right? So once everything completes, then it will send it, and you can give just the payload data, and the stack will build all the headers, right? It'll build and insert the Ethernet header, the IP header, the UDP header. It'll compute the checksums. It'll compute the lengths. It'll take care of all that. That's the plan anyway. For servers, the idea is pretty simple. It's pretty similar. You'd issue a request to the control streaming interface to open a listening connection specifying the port. The stack would return the context information again. Then when you get a packet from a remote host, the stack will give you a notification saying, hey, there's a new connection. Here's the IP address. Here's the port. And then the stack will provide the payload data to the client. And then the client can just use the information from the payload to send the TID TDEST information associated with the payload to send a response back to that client. You don't need to touch the address, so it doesn't matter if it's IPv4, IPv6. You don't need to keep track of that in the client logic. Just TID TDEST will send a response. Boom, done. And then the stack again will build the appropriate headers and send the frame. All right, so where do we sit now in terms of the status? Well, so the initial implementation is going to target 10 gig with a 32-bit data path. The parser and the deparser logic that I'm working on is likely going to be fixed at 32 bits. So for lower rates, like if you're running a 1 gig stack at 8 bits, then that'll be width converted up to 32 bits. At higher data rates, we'll need multiple instances of the parser and deparser stuff. And the parser and deparser, they're only looking at the packet headers. So it's actually not too bad from a buffering standpoint to, step and repeat this a few times. So I think for 25 gig, you would need 2, or for 64-bit 10 gig, you would need 2. For 100 gig with the, standard CMAC interface of 512 bits at 322 megahertz, I think you would need 8 instances. I'm going to double check my math on that. But due to how the clock frequency and packet rates work out, you only need 8 instead of the 16 you might think. If you take 512 bits divided by 32, that's 16. So I think it seems pretty reasonable, but we'll see. The other thing is that this is potentially a knob that you can tune. Like if you don't care about having full line rate receive performance with minimum length frames, then you can turn down the number and only put in 4 cores or something like that, and save a little bit of logic area. The parser logic that I have so far, it works in simulation, including VLAN tags, IPv4, IPv6, UDP, and TCP, and it also handles extension headers and TCP/IP options. And by handling, I don't mean it actually interprets the options, but it can skip over them and continue processing the packet. Unlike the old stack, where if anybody has any optional fields enabled, it just drops the packet. So that's definitely a significant improvement. The parser logic in parallel also computes the whole frame checksum based on the checksum fields in the TCP and UDP headers, which can be used to verify that the whole packet checksum is correct, which would be computed separately along with the length. It computes the payload length, which is potentially useful information for the application logic. And it computes the L3 and L4 header offsets. So if you want to do further processing of those headers, it helps to know where they start as opposed to having to reprocess everything. It also computes the RSS hash value, which is potentially useful for load balancing or whatever. And it also validates the IPv4 header checksum. So like I said, it works in simulation. I need to test it in the hardware to make sure it's going to work okay timing-wise. And I'm starting work on the deparser, which basically does what the parser does, but in reverse. It takes in a metadata block and then generates all the packet headers and computes all of the internal checksums and whatnot. So that's kind of where we stand right now. I don't have even a minimal example on an FPGA yet because I got to get enough of the plumbing in place to actually be able to send and receive some packets. Like I might stub out the the rules engine part in the middle that determines what to do with the incoming packets and whatnot. But I need to have more of the data path complete before I can actually test this on an FPGA. But yeah, so like I said, initially supporting 10G 32-bit, but once I get that done, then the idea will be to expand it to support, higher link rates and such. So I think that's about
What,
all I got for
what,
today. Yeah, this
what
point,
about fragment? Yeah,
what?
what about fragmentation? Sorry. Go ahead, go
Not
ahead.
supported.
Uh,
Not
But
supported.
but that's the point, right? So if you are doing somehow payload length, okay, now you can say that okay, it's supported for certain payload length. But now that you're calculating payload length, you kind of need to, because now I can keep on giving you some payload. You need to fragment and send that packet out and then create new packets for after a certain point, right?
Let me put it to you this way. Supporting fragmenting on TX is
Mhm.
maybe not too bad, but reassembling those fragments on
All right.
receive is a gigantic
Mm,
pain in the rear. So I'm just
yeah.
not going to support fragmentation at all. If you want to
Okay.
support fragmentation, maybe we can have some sort of a plugin interface that can handle that. That's not something I've put a lot of thought into. The parser logic can detect that a frame is fragmented, and when a frame is fragmented, it basically stops parsing the frame. So it doesn't even check to see if it's UDP or TCP once it's determined that it's fragmented, because it can only make that determination on the first fragment, right?
Yep.
Once you're out
Yep.
of the first fragment, then you don't have that header, right?
Hmm.
So what do you
Hmm.
do? Um, so yeah, I the idea is that I'm trying to keep this. I'm trying to start with kind of this core of functionality, right? We're going to get that
Hmm.
working first, and then we'll figure out how to expand from there. So fragmentation is like, way down the list of priorities to support.
Right, right.
Because I think under, 99% of cases, you're not going to be using fragmentation, right?
Yep.
TCP, you don't
True.
fragment TCP, right? You lower the MSS and then
Yep.
you send the
Yep.
whole packet. With
True.
UDP, I mean, I guess it's a slightly different story, but in general, I think you're just going to keep the messages below your maximum frame size.
Hmm.
Basically do something similar to what you would do in TCP. Otherwise, then you got to fragment and reassemble it. I mean, I think even reassembly is kind of terrible in software as well. It doesn't really matter how you do it; it sucks.
Mm.
So it's
Yep.
like, I mean, it's worth thinking about. Like, how would you even do, reassembly of fragmented stuff with a reasonable level of efficiency? Like, you need probably big buffers. You need complicated logic to keep track of all of the packets in those buffers. It's not great. It's doable, but
Right.
it's not great.
Right.
And whenever you start doing things like that, then you start introducing potential for massive reordering, right? Like you get,
Mm.
some, and also what happens like if you drop one of the fragments, right? So somehow you have to like time out your fragmentation context and drop all the fragments that you didn't receive, or that you did receive, right? So it's
Right.
tricky. And there's also all sorts of weird corner cases with fragments. I when I was just doing some searching around, I saw a number of references to, um, what happens if you have basically a packet that was fragmented incorrectly, where there's an overlap, right? And that
Mm,
apparently can cause problems if the stack doesn't handle that correctly. So, yeah,
mhm,
it it opens up all sorts of weird corner cases, and it's a pain in the butt from a logic perspective, and in most cases, it's not even used. So, um, now it's probably a different thing if you're talking about the internet at large versus an internal network inside of a data center or a building or something like that, where you're not going through nearly as many routers controlled by goodness knows who. Um,
mm,
but yeah, I think even there's another difference as well between IPv4 and IPv6. So with IPv4, it's allowed for routers to fragment packets, but for IPv6, it's not allowed, right? So if for
right.
IPv6, when a packet shows up at an intermediate node that's too big, then it gets dropped, and there's like an ICMP, I think, response that gets sent back saying, "Hey, that packet was too big for the MTU of this
Mm,
link or whatever. So you gotta
right.
you gotta make it smaller."
Send it back.
And
Yeah.
then the initial sending host is what's responsible for fragmenting the packet.
Mm, right.
So,
Right.
so yeah, at least for the time being, no fragmentation support, and
Right.
I don't foresee that changing unless there's a really compelling reason to do that. Um, and yeah, that's actually a good point because that'll definitely have to be a check that's done on the transmit side, and probably a parameter that's configured somewhere is, if you give it a payload that's too big, then that frame obviously is not going to be able to be sent, so it'll have to be dropped at some point. And then I guess the stack will inform the client saying, "Hey, sorry, had to drop your frame; it was too big." Um,
Mm,
so that's that's probably how that's going to have to work. But yeah, that is an important corner case to think about because as the header size changes under various circumstances, the payload size that you can use might also change. So you basically have to check that on a packet by packet basis to make sure it's good.
right. I had another question. So with the AGLX, you said that the 500 megahertz frequency is a problem. So I just want to know what are the pitfalls. So is it like they did not increase the frequency of the programmable logic, and so the data incoming is at a higher rate, and then now you need a huge buffers to accommodate that kind of frequency? Why is that a problem?
Well, it's a 1024-bit bus at 512 megahertz.
Right.
So yeah, I
Right.
guess you could do a width convert to 2048 and then drop it to 250 megahertz or something in the logic. But now you're dealing with a stupidly wide bus, and then that 1024-bit bus I think is already in four segments of 256. So yeah, the logic just gets super complicated. Um,
Hmm.
but the interesting thing about those devices is that at Gen 4 by 16, you can do 1024 bits at 250 megahertz, which is actually not terrible. So you might be able to support, if we can't do Gen 5 by 16, at least we should be able to do, I think, Gen 4 by 16. But yeah, the idea about saying I want to try to target that device natively is like, okay, well, instead of starting out at a lower speed and then having to rewrite, 90% of the logic because it doesn't close timing, we're going to start with the Agilex I-series device. We're going to start with this thing running at 500 megahertz, and we'll see if we can get that timing optimization from the get-go. And if it doesn't work, it doesn't work, but you got to start somewhere. And there's other
Right.
optimizations I think that are needed for the Agilex devices. Um, I know the Intel devices, they have these hyperflex registers in the fabric. Um, and those are potentially useful for getting stuff to run at a really high frequency. The problem with the hyperflex registers is that they don't have clock enables. So if they don't have resets either. So if you're inferring clock enables and resets on everything, then you're basically not using the hyperflex registers at all. You can't use hyperflex registers. And that's going to reduce the maximum clock rates you can hit and whatnot. So that's definitely one thing that I need to keep in mind as I'm putting the code together is that, well, I got to avoid resets and I got to avoid clock enables as much as possible, such that when you put this thing on an Intel FPGA, it'll actually use the hyperflex registers. And potentially I just need a lot more pipelining in certain areas. We'll have to see about that. But that's probably going to be a difficult problem to solve to get stuff running on the Agilex I-Series devices. But I got to
Hmm.
get it running on the UltraScale Plus ones first with the Corundum Lite before we start looking at the Corundum NG. Because that's kind of the way I'm envisioning this is we'll start out with the simpler design running at a lower speed. We'll get the driver mostly figured out. We'll get you know the FPGA implementation, figured out, and then we'll move up to the next level of performance, and we'll have to have some more optimizations. We'll have to do more stuff in parallel. And the 400 gig thing, I mean, because that also has to potentially support 400 gig on the Ethernet interface side, we might not even be using AXI Stream. We might be using something else that can do, multiple packets per cycle or something like that. So it potentially opens up a lot of cans of worms to hit those higher speeds. So we'll see about that. I
Mm.
think there's a lot of unknowns. Um, yeah, we'll see. I know I'm gonna have
Oh,
to rework a lot of the PCIe stuff to handle both the wider width as well as the higher clock speeds. So yeah, we'll cross that bridge when we get there. You're gonna say something else?
yeah. I mean, sorry. It's a totally different topic, but I was talking to somebody today about Versal, and few months back, I was looking into somebody came up to me for a design, and I was trying to use Xilinx interconnect IP, Axie interconnect IP,
Yeah.
and there was no such IP in the catalog for Versal devices.
I mean, they can't have removed it. It's got to be under a different name or something. It might be like Smart Connect or something. I'm not sure.
Yeah, I think it's a smart connect, but I don't know. So is
Yeah,
there a
somebody
huge
else was
difference?
asking about that. Like they in the IPI flow, they removed like a concatenation block or something, and it seems like there's a different way to do the same thing, because it's like concatenating two signals together. That's like a super fundamental thing that you're going to have to do all the time. So removing the block to do it without a replacement, they wouldn't do that, right? It's such an idiotic thing to do. So there has to be some other way to do it. And yeah, the smart, for AXI crossbar interconnection, there has to be a block for that, on Versal. It doesn't make sense that they would remove that because that's just HDL, right? So, if you
Hmm.
run it on UltraScale Plus, you should be able to run it on Versal. So I don't know if they might have a slightly different variation with a different name that's appearing in a different spot in the IP catalog or something, but it doesn't make sense that it wouldn't be there at all. Um, I don't know, unless,
Then I thought that are they relying on knock, because that doesn't make sense, right?
yeah, I don't think they'd be relying on the knock for that. The knock is more, I think, for
Or
interfacing
peripheral,
with, yeah, so the
yeah.
knock is more for interfacing with the hard logic and less about
Mm-hmm.
interfacing between multiple components on the FPGA. I mean, you can use it for
Mm-hmm.
that, but it's like if you want to talk to the DDR controllers, the only way to do that is through the knock, right? If you want to talk to the AI cores, I think the only way to do that is through the knock. If you want to talk to the PCIe doesn't have to go through the knock, I don't think. Um, the hard logic on there, right? The PS basically. I think you can choose if you want to talk to that directly or talk to that through the knock. Um, but yeah, to be honest, I'm not a huge
Fan of Versal.
expert on.
Come on.
Well, I'm not a
Okay.
huge expert on Versal because I've read some of the documentation. It's the kind of thing where until you sit down and you actually start doing stuff, you don't really fully appreciate all the details of the architecture, right? So I've read over a bunch of stuff. I have some idea of what some of the high level limitations are, um, but when it comes down to how you actually do stuff on there, I got to build some
Mm.
Versal designs, to get a
Mm.
a better feel for that, and I haven't done that yet. So at some point. I might have a better understanding of how that works. Yeah, it's like the big thing with the VTK 5000 boards was just figuring out how to run a design, period, from Vivado on there. It's like if I can't run a
Mm.
design on here, then these things are just paperweights. But if I can run a design on there, okay, well now I can stick these on the old bookshelf, or on my mountain of FPGAs. And then at some point, when I have the time and the motivation to work on these things, right? Once some of these other to-do items are knocked out, then you know
Mm,
we can figure some stuff out on those guys. Um,
mm,
but yeah, so it's like if I can't load a design on there at all, it's like what's the point? But yeah. And I definitely learned quite a bit about Versal just by trying to get a design running on there because there's there's a lot more moving pieces in there versus the normal Xilinx just pure
mhm.
FPGAs. Um,
Right.
I will say there are some things that are kind of nice about Versal compared to some of the other devices. With the Zinc devices, you cannot generate a flash image from Vivado and flash the board, right? You
Mm,
have to go through Vitis to generate the
mm,
FSBL and yada yada yada, and then you flash the FSBL because the thing boots like
mm,
an SoC. But it seems like for Versal, they've actually I guess what they've done is they've kind of pulled pieces of this software stack into Vivado. So Vivado is now, as far as I can tell, capable of generating a basically an FSBL or that early firmware image stuff.
mm,
And then it bundles all that into this thing called a PDI, and then you can load that via JTAG and presumably also flash it. I haven't tried flashing it, but presumably you can also flash that. So that's actually kind of nice. It would be really cool if they could backport that to the Zinc devices, but that's probably asking too much.
right.
Anyway, does anyone else have any questions or comments? I mean, not saying that there's anything wrong with this conversation, but if anyone else has any questions or comments, go ahead and fire away.
Uh, acho que it's the first time I appear. I saw a lot of videos from YouTube and uh, this I didn't get deep inside your project, but what I know is that you can port this Corundum to Cisco former Xenic boards, and I'm a user of Cisco Exonic boards for maybe 5 years, and
Nice.
yeah, uh, and I know that Cisco promised to allow their framework with 25 gig
Hmm.
speed for a long time, but since now it has not support of it. So
Ah,
I
man.
look at so I look at this project, trying to see if I can maybe one day upgrade the to a 25 gig speed without needing to throw away all the boards we use here in commercially. We use it here commercially. So
So you're using which boards? The X100s, X25s? Or whatever the heck
yeah,
the Cisco part number is for those things. Do they have
yeah,
SFP28s or QSFP28s?
yes. I used F4s, but now we use only F20, X100.
Okay, so the dual QSFP version.
Yes.
Okay.
It has V5P2, but the main body I use now it's X100.
Okay. Oh, so you also have
So
the V5P, right? So that's those are different board, I guess, right? So that's I can't remember if they
yeah,
can't remember what the part number
like
is for those things, but yeah,
yeah,
so
yeah, yeah, X100 is like a Kintex
yeah, KU3P,
Ultra
I
Scale
think. Yeah.
Plus, and V5P is a Vertex Ultra
Yeah,
Scale
yeah.
Plus.
So but from the same kind of series.
Yeah.
Okay.
So I just want to know if you had have good results using like Cisco boards with 25 gig.
Right. I mean, for the most part, with Corundum, there's not really much dependence on the specific board, right? Because everything is on the FPGA, right? The PCIe goes straight to the FPGA. The Ethernet interfaces go straight to the FPGA. So basically, with very few exceptions, all the boards basically perform more or less the same. So it doesn't really matter if you're using the Cisco board versus, a Bitware board or whatever. I mean, I guess there might be some differences, like in terms of how you update the firmware or something, but the Cisco boards are, probably some of the better supported boards, that support all of the various features. It's like I think the only shortcoming on those boards is that the oscillators are not tunable, um, which doesn't matter for most applications. But if you're, like I'm doing this timing stuff, you need to be able to do fine frequency adjustments for timing. And if the oscillator is not programmable, then you can't do that. Um, but other than that, it should work just fine at 25G. I guess the question is, what exactly are you doing on these boards, right? Because I know the FDK from Cisco is designed for super low latency stuff. Um, so do you need that kind of latency performance, or just kind of at a high level, what are you doing with the cards, right? So
Yeah,
if you
yeah,
need
I
super low
use
latency, Corundum is not optimized for super low latency. Um,
yeah,
so that could be a problem.
yeah,
But
yeah. I use it like I use FDK and I use uh things related to low latency stuffs and
yeah, so I guess
but
that might be worth a some further discussion to figure out what your requirements are in terms of latency and such, to figure out whether Corundum would even be appropriate. Um, because yeah, if latency is too high, what's the point? But I guess there is also a trade-off between, latency and link rate. So I know one thing, maybe one of the reasons that they don't have the 25G design out yet is 10G is almost kind of a sweet spot in terms of latency, because you can play some tricks to basically get the latency, particularly low. If you move to 25G, yes, it's a higher link rate, but in a lot of cases you need FEC, which, is not good for latency. In a lot of cases, you end up needing to run with a wider internal data path, right? Like I think on the Xilinx devices, really your only option is to run 64 bits at 25 gig. If you run at 10 gig, you can easily run at 32. And there's some people that even run at 16, which requires like overclocking the transceivers beyond their spec. But you don't need to overclock by that much to hit that. And then that really reduces the latency, right? So there's a bunch of
yeah,
tricks you can play at 10 gig that you can't play at 25 gig. So, and I think for at least for financial stuff, I don't know how useful it is to have that additional, you know, 15 gigabits per second worth of bandwidth, right? So I think a lot of those guys are like, well, we like our 10G solution. We don't need the additional bandwidth. We're just going to roll with that because we can get the latency a lot lower than if we did it at 25 gig. Um, so I don't know exactly what Cisco is doing internally with their 25 gig designs. I know they've been working on it for a long time, but I thought they would have released it by now. It's interesting to hear that they haven't even released it yet. So yeah, that's yeah, depending on what your latency requirements are, that would definitely determine um, what
yeah.
makes sense. Because that might be a trade-off. Like, okay, if you want to do 25 gig, well, maybe it's going to have to be higher latency. You know, is this for financial applications or something else? Just out of curiosity.
Yes, it's for financial
It is for
applications.
financial. Okay,
Yeah.
and you guys are actually using 25 gig. That's interesting. Okay.
Actually, uh, I don't need like 25 gig for like trade things like trading, but there are some projects that is not related to trading exactly, but it's inside the financial world that maybe
Right.
I will need to use the 25 gig.
Ah, okay, okay, I see. Are those projects latency sensitive?
Yes,
Yeah,
yes,
okay.
yeah,
No such thing as a free lunch. Okay.
yeah,
Well, I guess Well, we'll have to ruminate on that. There might be some opportunities for modifications to Corundum to reduce the latency, right? With the I have had some people asking about ways of basically having the CPU either write the packet or at least write the descriptor directly to the hardware, which would cut out a whole DMA round trip with sending packets. And that hasn't been a priority for me as a researcher because I don't really need that kind of capability. But if this is stuff that you guys need, for your company, and you guys would be interested in, licensing the design and, paying to have some of these features implemented, then that's definitely something that we could talk about. Although it's probably going to be a ways down the road. It'll probably be part of the, rewritten Corundum NG or something, as opposed to the older, MIT version of Corundum. But at least supporting, the X100 cards, that should not be a problem.
Okay, now I want to ask you something, maybe not related to Corundum, but
Yeah, sure.
when I started working with FPGA things, I used to uh, I need to use like a PCI Express framework that is from your university too. They called it RIFA.
All right,
I
yeah.
wanna know if you were part of this project, because I used it for a while in the beginning of my career. So
I know one of the guys that built Rifa. This might even be like the main author, you know, bumped into him a few times. But no, I had no involvement with Rifa. Yeah, when I started working on Corundum, I did actually look at Rifa as a potential option for, for using in Corundum, but I ended up, rolling my own setup because Rifa is my understanding, at least, it's quite similar to XDMA, where it's really intended for, compute offload type applications and not so much networking. So, while it is a PCIe DMA engine, and it certainly has use cases, it I didn't feel it was appropriate for Corundum. So I ended up going in a different direction. But yeah, I am familiar with the project on
I
some
guess
level.
this is a old-fashioned project right now, right? As I remember, it's like for just one gig and with a old PCI version too.
Yeah,
I don't think it's yet supported. I don't know.
yeah, so I think Rifa like targeted a bunch of much lower end parts and older parts. I mean, Rifa predates Corundum by a few years. So, like when I started working on Corundum, the I basically just targeted the ultra scale series because that was what was available. And it's like, well, all right, well, if we have the budget to get the ultra scale devices, they're going to be faster than the 7 series ones. So we'll start with that. And that's one thing that I've realized is that the timing actually worked out very nicely, right? Because with like the 7 series devices, even getting 10 gig Ethernet working on those is quite a bit more complicated because of the way the transceivers are built, right? You don't have the asynchronous gearbox mode. You only have the synchronous gearbox mode, which complicates the logic to interface with it and that sort of thing. But for the ultra scale devices, you have the asynchronous gearbox mode, and that makes the logic sitting on top a lot easier. So, and also even the PCIe stuff, I've been surprised at how, little additional, fine tuning I've needed to do to get stuff to work on the ultra scale devices, even at 250 megahertz. I thought this was going to be just a complete bear to get it to close timing, but for the most part, it more or less just works, even with some rather crappily coded components. So, I mean, we'll have to see with moving up to the higher speeds, but yeah. If I was working on 7 series devices, different story, right? On the Ultra Scale Plus, tends to close timing just fine. On the Net FPGA Sumi, which is a 7 series, yeah, that's a different story. That one fails timing quite badly most of the time with the Corundum design. So yeah, if I had started this project a few years earlier, working on, 7 series or Stratix 5 or something like that, I think it would have been a much bigger pain in the butt to get everything working. So Yeah, it seems like Rifa targeting some of the older parts. Well, not necessarily older, but also lower end. Like I think they support things like Cyclone 5, right? Um, which is a much
I
slower
used
part.
it in Net FPGA CML one.
Okay.
I
All
don't-
right, and then that's a one
yeah,
gig board. So yeah,
the previous one from Net FPGA Sum you said
right.
a long time ago.
Yeah. Yeah, I mean that project's been out for a while. I don't know what the current status of it is, if they've updated it for newer boards or whatever, but yeah, unfortunately, projects need a lot of maintenance to keep running as new parts are released and older parts are deprecated. I mean, even Corundum, it supports a bunch of boards that are now deprecated, right? Xilinx scuttled a lot of their Alveo boards. You can still get them used, but I'm not even sure what I need to check on what their current lineup is. I don't think Corundum supports all the current ones, unfortunately. I'd like to support a V80, but I don't have 10K to drop on one of those things.
So,
Well, nice talking with
uh,
you. If you have any other questions, feel free to contact me on Zulip or whatever, and we can discuss. So
okay. I think I need to uh, go
you need
deep
to
in
ruminate on
internet.
some of this stuff. Yeah.
Yeah. It's a big project. Uh,
Yeah.
yeah. And congratulations because the few things I saw, I really like what I saw.
All right. Well, it's good to hear.
Okay.
All right. Does anyone else have any questions or comments? Or I know I see Tobias and Ulrich on here. I don't know if you guys have any questions or comments, anything you guys want to add or subtract.
All this
Oh, by the way,
uh
sorry. Go
all
ahead, go ahead.
this thing is done only by you, or you have maybe supporters.
That's just me. Yeah, for the most part.
Very
I mean,
very
there's there's
incredible.
there's, there's been a couple of patches, contributed by a few people, like the Ulrich and the folks at MLE are pretty familiar with Zinc, so they contributed some stuff related to Zinc device support. But yeah, all of the outside of some stuff like that, all of the core logic, all the DMA infrastructure and everything, that was all me. So as well as a lot of the verification stuff, right? I wrote a bunch of Coco TV extensions for Ethernet and PCI Express and whatnot. So, um, you know, without that, the rest of the project wouldn't be possible. I put all that together too over, you know. I mean, I guess those didn't start out in Coco TV. They started out in MyHDL. So I didn't write the Coco TV extensions first because I did everything in MyHDL first. Um, but yeah, so those things basically predated Corundum. Without those, the rest of the project wouldn't be possible. So yeah, it's just me, but I've been working on this stuff for quite some time, and it builds up little by little, one brick at a time.
Oh, so while we are talking about support, so for X3522, right?
Hmm.
Uh, are you so so have you built Corundum? I don't think so, right? Because after you debugged,
Yeah, I
I don't
built
think you
it,
touched it
tested it, it
again.
works.
Oh, okay.
It's basically the board is almost identical to the SM1000 or SN1022 thing. It's the same part,
Hmm.
very similar pinout, same transceiver sites that are used, same
Hmm.
um, board management controller thing. So I built it, I tested it, it works. I don't have support in the firmware update tool yet to be able to flash it. I can't remember if I pushed the design yet or not. I guess I
The
should take a look.
design? No,
I
in
guess
the
not. Yeah. All
in
right.
your first name, yeah.
Um, yeah, I guess I'll take a look at that. But yeah. So yeah, the design works fine. You can run it on there. It's that's fine. It's more just I don't have the firmware update support fully implemented because I gotta double check on that. I had to add a bunch of code to the firmware update thing to support accessing some of the non-volatile configuration registers on that thing. So I think I also want to add some additional capabilities to that to where you can like dump just an image of the entire flash. Right now, like you kind of divide it up into flash partitions that are exposed through a register that the the firmware update tool reads. But it would be useful to just say, hey, give me the whole friggin' flash as one dump. So for something like the X3522, you can back up the entire flash. And then you can clear out the sector protection bits and whatnot, and then write, a new image to it. So
But
to
there are two
convert it to
flashes,
Corundum,
right?
and then you can convert it back later. What?
But there are two flashes, right? Secondary flash and a primary flash. No,
Are there?
I think there are two flash.
How do you
So
switch? How do you switch between the two? I
yeah,
think
no idea.
I think that involves going through the BMC on there. So yeah, there's still some unknowns about those boards. So I don't know. I don't know the best way to support that stuff.
Mhm.
Because I even though I have the schematic, that kind of stuff is not really documented, right? Because that's more in terms of how the BMC works internally to switch between the two. There might be a command
Mm,
for it, but I'm not sure what it is.
mm.
Yeah,
Because
I can confirm that there are two flashes, at least in the Alveo U45N. I've seen it in the schematics, but I haven't checked. I haven't switched between them.
yeah, I
No,
remember that from looking
as
at the U45N, and there's definitely two flash chips on the X3522 as well.
yes.
And when I probed it, I think to determine the flash key, I think I was actually probing on the level translators. Well, no, I wasn't probing. I found test points, but because the flash chips are BGA, you're kind of screwed. You can't really probe the flash chips directly. So I'm like, oh, there's the flash chips, and oh, there's level translators right over here. And then I think when I was finding those pads, I can't remember if I did that with a multimeter first, and I'm like, well, I think these level translators are for the flashes, so let's just go around to the multimeter and beep out all the test points and see if I find one that looks interesting, or if I just went around with a scope probe until I found, something that looked like QSPI. I probably did a combination of the two, but yeah, there's definitely two flashes on there, and it's definitely not dual QSPI. It's definitely this muxes to switch between the two.
Mm. So as far as I remember, last time when I was using Vivado, there is an option to change the while you upload a MCS file, you kind of select one of the flash as a bootable flash or something like that. So
You
something I
select
was dealing with. Sorry.
so what exactly do you select?
After you flash our MCS file
Yeah,
through Vivado, you kind of have an option to select, make it as boot or something like that. I don't remember.
you're talking the
But
boot from configuration flash button.
yes, yes.
Oh, well, that just resets the FPGA.
Okay,
Yeah.
okay, got it.
So instead of power cycling the board, you can just do boot from configuration flash, and then the FPGA attempts to boot itself from the flash. That's literally all it does. But
Mm,
it's useful. It's very useful.
yeah.
But yeah.
Okay, I'll see. So if I'm able to change from primary to secondary, then we don't need to dump the. Yeah, again, dumping is will be helpful, but then
Yeah.
then again, you don't need to dump. You can change either of the nicks.
Right, right.
Given that they don't use secondary for some XRT image stuff,
I
possibly,
don't
right?
think
Because
so. I
they
don't
have
think so. It's a pretty
they,
big flash. So I think the way it works is well, actually I have no idea how so the problem is the non-PV version of these things, they're not really designed for having a separate image uploaded, right? They're just designed for running their image. And I know it is built from several pieces, right? If you look at the contents of the flash, you can see there's multiple bit streams in there. But I don't know exactly how it works, basically. So yeah, I'm guessing it must have it probably has a similar setup where it loads some sort of top level image, and then there's probably multiple partial reconfiguration blocks in there. And I don't know if it will swap out depending on what link rate you're running at or something, what's in the various blocks, but yeah, because we don't really have any visibility to what's going on there. I know the firmware for some of the other components sits in the flash. I can't remember if the firmware for the board management controller sits in the flash, but I know the firmware for the microblaze core in the FPGA sits in the flash. But I think they call it the NMC firmware. So that's in there somewhere. And that's loaded by the NMC core when the FPGA starts up. But
Okay.
yeah, so I think there's quite a bit of stuff in the flash, and I don't know how the locations are defined. There might be some little table somewhere that indicates, in the flash where stuff is. That might
Okay.
not, it might just be hard coded. I don't know about that. Like maybe the bootloader for or not so much the bootloader, but like the for the microblaze core, whatever its startup code is
Yep.
that's on the
Yep.
FPGA, it might just know, where it should look in the flash. But yeah, so there's quite a bit of complexity with the X3522, and if you're gonna add some additional image to that, I don't know where you put that necessarily because I don't know what the layout is. For the X3, they have obviously a different image that gets loaded on there, and I think it probably looks more like the other Alveos, where it's just at the bottom of Flash, they just have one image, and then there's going to be a certain point, and then above that, that's where you can put your user image. I don't know if it's the same split point as for normal Alveo or how it works really, because I don't have the firmware package for the X3.
All right.
But yeah, I mean, I wouldn't be too concerned about that because you can always just dump the flash and back that up
True.
somewhere, and then you can always just put it
True.
back later. So
Yep.
yeah, the big thing is knowing how to unlock the flash. If you can't unlock the flash, then you're screwed. But if you can unlock the flash, okay, then we can unlock it. We can do whatever we want, and then if you flash the X3522 image back on there, I actually don't know if it'll lock it. It'll probably lock it after you do a firmware update with the X3522 image running on there. I'm not sure about that.
I need to go, and thank you for your answers, Alex. It's nice. It was a pleasure to talk with you
Great
guys.
talking with you. And thanks for
Bye.
dropping by.
Thanks. See you.
All right.
Okay.
Well, if nobody else has anything to talk about, then I guess we'll adjourn for today and talk to you guys maybe next week, if not in a month. Hopefully we'll have some more interesting stuff to talk about. Hopefully I'll have the IP stack partially working at least and can provide some numbers on that. That would be cool. All right. Well,
Thanks and bye.
all right. Talk to you later, Tobias.
Thanks. Bye-bye.
All right. Talk to you later, Ulrich.